In this video, I'm going to be talking about sound. I'm going to be discussing what it is, how does it work, what affects its speed, tone, and volume. So to start off, let's take a picture, look at this picture over here to the left, and we have a speaker disrupting the air molecules and sending a sound wave over to the ear. So what happens is the source of any sound wave or any wave in general is a vibration. And as these vibrations occur, it disrupts these air molecules and it sends vibrations and energy through the air. So what happens is, as this speaker vibrates back and forth, as it pushes forward towards the ear, it creates these areas of high pressure where the air molecules are bunched together. And then as it vibrates back away, it creates areas of low pressure where the molecules are a little bit more spread out. So the way that a sound wave moves is through a series of high and low pressure regions to eventually vibrate the ear and the eardrum, which we'll discuss a little bit later in this part over here. So as it moves, it does not move like a transverse wave. It doesn't actually move up and down. It just moves directly out in all directions, which is known as a longitudinal wave. So let's go ahead and label some of these different terms, and then we'll come back and follow up. So as I said earlier, the speaker is vibrating side to side, and as it leans forward towards the ear, it creates area of high pressure known as compressions. And then as it leans back towards the left, it creates areas of low pressure that are called rarefactions. So depending on the frequency of the sound wave, it creates a different amount of high pressure and low pressure regions per second. And that is known as a longitudinal wave because the wave motion is parallel to its velocity. Okay, so this diagram underneath is a transverse wave that wiggles up and down, and its wave motion is perpendicular. So an actual sound wave doesn't move up and down, although there are digital representations of sound waves that look like that. But in reality, it really moves out in all directions straight out with these high pressure and low pressure regions. Now, as these high pressure regions strike the eardrum, it causes them to be pushed in. And then once a low pressure region reaches the eardrum, it allows it to come back out, and then so on. So it moves back and forth to vibrate in order for you to hear certain pitches and frequencies. So what makes a sound the way that it does? What creates its tone? What affects its speed? And what affects its volume? So with the tone, that is dependent on the frequency of the wave, how often or how frequently it vibrates back and forth. So it could be a vocal cord, it could be a guitar string, it could be knocking on a door. So depending on how frequently that object vibrates back and forth, that will make your eardrums vibrate at a different frequency, therefore causing you to hear its different pitches. So the frequency and pitch are directly related, and a lot of times you can consider the mass being part of that relationship, where the mass and the pitch have an inverse relationship, because typically things that have smaller masses or that have more tension, that shake back and forth more quickly, create higher pitches, and things that are larger with less tension tend to move back and forth a little bit more slowly, and then their pitch has decreased. So what affects the speed of a sound wave? So changing the speed of the sound wave isn't quite as easy or as common as changing the frequency or pitch, but you're basically changing the medium. The medium is the matter that the wave travels through. So if you change the density of the medium, then the speed will change. So when you're sending sound waves through a particular medium, it's difficult to change the speed of it. So you can't change the pitch of your voice, you can't yell louder. That's not going to change how quickly the sound wave travels from point A to point B. So it just all dependent on the medium. So what kind of matter is the sound wave traveling through? Now, contrary to what a lot of people may think, the speed of sound is much greater through solids than it is through a liquid, than it is through a gas. And you have to remember that sound is not a physical object. It's energy, it's vibrations. So typically, if you're sending a physical object through solids, liquids, or gases, it's easiest for it to travel through a gas, therefore it would have the greatest velocity. But that's the opposite with energy. So because energy and sound waves are these vibrations that pass through the air molecules, if those were more tightly compacted to each other, that vibration, that chain effect of one air molecule bumping into the other one, is a lot faster and allows the sound wave to travel a lot more quickly. So if you take a look at some type of matter in its three different states, it's going to be the same atomic, it's going to have the same atomic makeup, but with a solid, the molecules are going to be more tightly compacted, and then with a gas, they're going to be more spread out. So it's sort of like a domino effect, to where if those molecules are really, really close to each other, if you vibrate one, then it's going to hit the other ones more quickly, as opposed to the gas that's a little bit more spread out. And as they bump into each other, it's going to take them a little bit more time to pass on that energy. One of the other factors that changes the medium is just taking a look at that temperature, even though there's not a change in state from a solid, liquid to a gas. For example, if air has its temperature increased, it actually increases the speed of the sound, because the air molecules are going to be loaded up with a little bit more energy. So as you pass that sound through, it's going to travel a little bit more quickly at those high temperatures. And if that temperature is lower, it's going to cause the speed of sound to drop. Now, finally, what affects the volume? The effect of the volume is not based on how quickly it vibrates or what it travels through. It's basically just how large the vibration is. So when that speaker is vibrating back and forth, if it has a larger vibration, a larger range of motion, it's going to create areas with greater pressure and lower pressure. So when they strike the eardrum, it's going to cause more movement, therefore having you hear a louder sound because more energy is passed on to your ear. Now finally, just kind of taking a look at the ear. As we said before, these high and low pressure regions strike the ear. The high pressure regions cause the eardrum to move in, and then the low pressure regions allow it to come back out. And then whatever frequency the source is providing, that's the same frequency that the eardrum wiggles back and forth at. So as these sound waves enter, they move this eardrum back and forth that's connected to a series of bones. And what happens is, as that eardrum vibrates back and forth, it vibrates these series of bones back and forth, and it basically works like a little hammer. One of the parts that is actually called the hammer. And what it does is this little hammer bangs on the inner part of the ear where the cochlea is. So as it strikes the inner part of the ear, there is fluid, and those waves of energy are sent through the fluid that vibrate a bunch of different hair cells. So inside the cochlea, there are thousands of little hair cells, and the smaller hairs that are a little bit more stiff have a higher resonating frequency. So once those high-pitched sounds come in, they only wiggle certain hairs, and those ones send signals to your brain that you hear high-pitched sounds. And then for the lower frequency sounds, those little hair cells are a little bit more flexible, so they have a lower resonating frequency. So those ones that naturally wiggle back and forth a little bit slower, once those low sounds come in, they're going to wiggle those little hair cells, causing them to send signals to the brain for you to hear those. So we have basically thousands and thousands of these little hair cells that can work simultaneously, and each of them have their own job of picking up different frequencies, so you can hear all different types of pitches and musical notes, and you can also hear them simultaneously. So to sum things up, we have a sound wave that causes energy to pass through the air because of vibrations, and as it passes through the air, it causes high pressure and low pressure regions, and those high pressure and low pressure regions will vary in frequency depending on the pitch, and they'll also vary in speed depending on what kind of medium it travels through, and also vary in volume based on the size of the vibration. Once those strike the ear, that wiggles the eardrum, which causes these bones to move and then bang on the inner part of the ear. And as that liquid has those vibrations come through, it wiggles a little hair cell of a certain stiffness in order to send a signal to the brain so that you can tell what kind of pitch and what kind of volume to detect from the sound source. I hope that was helpful in helping you understand what sound is, how it works, and the different effects of its speed, tone, and volume. Thank you for watching and listening.